Today we're going to talk about two topics from geometry, and the first one has to do with square roots and the Pythagorean theorem. So first we need to look at what a square root means. So a square root of a positive number a is the positive number b whose square is a, which is a little confusing. So let me simplify that a little bit. So I'm going to pick a number, say 3. 3 squared is 9, because 3 times itself twice is 9. And so a square root would be like the reverse. I would say, well, the square root of 9 is 3. So we're going to look at a few of those to be familiar with. So for example, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So I would say for sure those first two rows you need to have like down, and they should be pretty quick. The first 3 rows would be ideal, or by rows, sorry, I mean columns. So if you want to like screenshot this or take a picture, these are good to refer back to. But now what we're going to do is we're going to actually use those square roots. So first we're going to practice. So the square root of 81, that's basically saying what squared is 81. So it's saying like what number to the second power gives me 81. And so that's just going to be 9. Square root of 1 over 25, well, there's one way to think about it. And that way is just thinking about, well, what would be to the second power? What to the second power would give me 1 over 25? And I get it this way. The way that I prefer to think about it is since both the 1 and the 25 are under the radical, so this symbol here is called a radical. So I can rewrite that, giving both the numerator and the denominator their own radical. So I can write it this way, or maybe picture it this way in my head. And now I can see, oh, well, the square root of 1 is 1, and the square root of 25 is 5. So I can get it that way as well. 1/5 either way. So the square root of 9/64 would be the square root of 9 over the square root of 64. Which is going to give me 3 over 8. Or I could just think about what times itself gives me 9 over 64. So either way, I get the 3/8. Okay, so now we're going to actually start to use what we know about square roots to estimate square roots. So if I were to look at square root of 58, that is not what we call a perfect square. So if I think about two things I do know, I know the square root of 49, and I know the square root of 64. Therefore, the square root of 58, I know fits somewhere in between there, because 58 is in between 49 and 64. So I know the square root of 49 is 7. I know the square root of 64 is 8. So I know the square root of 58 should be between 7, and it should be between 8. So I can actually evaluate that on my calculator. I can estimate, and I get 7.616 approximately. The square root of 58 is actually what is called irrational, meaning I can't write it like as a fraction. I can't write it without having to round. So for square root of 13, I can use that same principle, and I can say, well, square root of 13 is in between the square root of 9 and the square root of 16. So it's somewhere in between these two numbers, because 9 is in between 13 and 16. I know the square root of 9 is 3. I know the square root of 16 is 4. So I know, without a calculator, that the square root of 13 is between 3 and 4. If I type into my calculator, I get an approximation. And you might want to pause it and try the same for the square root of 89. You're going to get approximately 9.434. So now we're going to apply those square roots using the Pythagorean theorem. So the Pythagorean theorem has to do with right triangles, and a right triangle means a triangle with a right angle, a 90-degree angle. So anytime you have a right triangle, no matter how it's drawn, you have 3 sides. So the 2 sides that make the right angle are called legs. So that's important. And then the side across from the right angle is called the hypotenuse. And so when you're using the Pythagorean theorem, it's very important that you correctly identify which two sides are legs and which side is the hypotenuse, because the hypotenuse is always going to be the longest length, and that's also going to tell us how to use our formula. So here we have what's called the Pythagorean theorem, and that says that a squared plus b squared is c squared, where a and b are the legs. So I prefer to write it as leg squared plus other leg squared equals hypotenuse squared. Takes longer to write, but you get the idea. So let's just practice. So here we have a right triangle. It should be labeled like this to tell me it's a right triangle. So it said find the length of the hypotenuse. So I'm looking for the hypotenuse, that side across from the right angle. That is the side that I do not know. But one thing I know before I start working is that the hypotenuse is supposed to be the longest side. So I know my answer should be more than 16. So when I go to start calculating it, here's my Pythagorean theorem. Leg squared plus other leg squared equals hypotenuse squared. Now I'm going to replace those variables with numbers. Leg squared plus leg squared equals hypotenuse squared. And now I'm going to evaluate. So 12 squared, so 144. 16 squared is 256. So I get 144 plus 256 equals c squared. So you are welcome to use a calculator here, but 144 plus 256, I get 400. And so here we come back to those inverse operations we've been doing all semester. So I don't want c squared, I want c. So to undo squaring c, I square root. So to undo that square, this 2, I square root. Because when you square root, these are inverses, and I'm left with just c. So when I square root, I have to do it to both sides, and I end up with c equals 20. So the hypotenuse is 20, and it makes sense. It's longer than the longest leg. Also, I'm sorry if you can hear my dog breathing on me. So here we have another right triangle. And again, we're missing the hypotenuse. I would encourage you to pause it, try it, and then unpause and check your answer. So here again, I notice I'm missing the hypotenuse because it's across from the right angle. The legs are the two that make the right angle. So here's my Pythagorean theorem. A and B are the legs, C is the hypotenuse. So I'm going to replace them with my values, my known values. 22 squared and 48 squared, I would definitely type in my calculator. So you can actually type 22 times 22, or there should be an exponent button on your calculator. So bigger numbers this time. So now I'm going to add 484 plus 2,304. And now, to get c all alone, I undo squaring by square rooting. What I do to one side, I do to both. So this is my next step. Square root of 2,788. There should be a square root button. If you have a scientific calculator, and you should, there's a square root button on there. You might want to pause and look for it, but it is on there. So I'm going to get 52.8. It said to round to the nearest whole unit. So up here it said round to the nearest whole unit. So I'm going to round that up to 53 just because it told me to on this problem. So now we're going to look at an example unlike the first two. So the first two, we were missing the hypotenuse in both. So now I'm going to look at an example where I'm actually missing one of the legs. And so this is going to be the same formula, Pythagorean theorem, but my unknown is going to be either A or B, and you get to choose. So here I have leg squared plus leg squared equals hypotenuse squared. But this time, my unknown is either the A or the B. You can choose whether you put A or B as your variable, that's fine. And so before I get too far, I notice my hypotenuse is 9. Should be the longest side. So whatever I get over here, it should be less than 9. Because the hypotenuse should be the longest. So if my answer is more than 9, I know I messed up. So here, I'm going to go ahead and replace 3 squared with 9. And I'm going to replace 9 squared with 81. So here, when I'm solving for b, I've got a little extra work to do. I first need to get rid of this 9 by subtracting it from both sides. So that gives me b squared equals, and then I would do 81 minus 9. We get 72. So I don't want b squared, I just want b, so I'm going to take the square root of both sides. That is the inverse of squaring, is square rooting, so that would just give me b equals square root 72. And I know the square root of 22 is between 8 and 9, just based off my estimation examples I did earlier. So I'm going to look, I would type it in my calculator, and I get approximately 8.49. And so here it said give the exact length. So my exact length is going to be this, b equals square root 72. That's exact. As soon as I type that in my calculator, I have to round. The 2 decimal approximation would be this. And so notice my answer is less than 9 as I expected it to be, because a leg should be smaller than the hypotenuse. So here we've got a word problem. A football field is a rectangle measuring 100 yards by 53 yards. I'm going to draw a picture right off the bat. I'm going to draw a rectangle. So with a rectangle, something just to remember is that a rectangle, all 4 angles are right angles. So I'm going to sketch that. Really, I'm just going to label these 2. And so notice when I draw the diagonal here that I just created 2 right triangles. So notice I now have 2 right triangles. So on this right triangle, I have 2 sides. So I notice that this is 100 yards and then this is 53 yards. So I have both legs of this right triangle. So it says draw a diagram and find the length of the diagonal. So when I look at the length of the diagonal, that is my unknown. Maybe I should call it C just for uniformity here. So it said draw the diagram, find the length of the diagonal. So the hardest part is to draw the diagram and recognize I'm just dealing with a right triangle. Now that I know I've got a right triangle, I say, well, what am I missing, a hypotenuse or a leg? I'm missing the hypotenuse, so I'm going to use my Pythagorean theorem, and I'm going to replace my 2 leg values, A and B, with 153. I'm going to square those. It's perfectly okay to use a calculator. 53 squared is not something I know off the top of my head. So notice, I should have said this from the very beginning, C should be more than 100. The hypotenuse is always the longest of the 3 sides. So as I'm doing my math here, I can check. So I'm going to add 10,000 and 2,809. I want C all alone, so I square root both sides. The square root of 12,809 is approximately 113.176. And then I'm going to look and say, well, how did it ask me to round? It said round to the nearest yard. So that's going to be about 113. Ew, it says feet. Please ignore that. 113 yards. So for the next section, 7.4, more geometry, we're looking at congruent and similar triangles. So congruent triangles, congruent means exactly the same. So if 2 triangles are congruent, that means they are exactly the same shape and size. That means they have the same 3 side measures, same 3 angle measures. So notice these 2 triangles are exactly the same. They're 6 by 11 by 9, 6 by 11 by 9. So the word congruent means exactly the same. Here in a little bit, we're going to talk about the word similar, which means proportional. So One way to prove that triangles are congruent is something called angle side angle. And what that says is if you have two triangles and they have an angle congruent to each other and then a side congruent to each other, that 14 and that 14, and then another angle congruent to each other, that is enough to prove that those triangles are congruent. It's called angle side angle. So since they have this matching angle, this matching side, this matching angle in that order, that is enough that I can prove those two triangles are congruent, exactly the same. I have enough information now to know that B will be the same as E and so forth. So that's angle side angle, and notice the side is between the two angles. Another way to prove triangles congruent is called side side side. So if all three sides of these two triangles match up, they're exactly the same. So we have the 7 on both, the 8 on both, and the 9 on both. That is enough to prove those two triangles are congruent, exactly the same. So because the sides are the same, I know enough to know that the three angles are also the same. And that is called side, side, side. All three sides are congruent. Therefore, the triangles are congruent. Congruent meaning exactly the same. And then the next triangle congruence theorem is called side angle side. And it's probably just what you thought. I've got these two triangles down here, and I can prove they're congruent because they share a side, same side length, same angle measure, that 50 degrees, and then again the same side, 14. So that is side angle side congruence, and it has to be in that order: the side, then the angle, then the side, right in a row. So now we'll look at a couple examples. It says determine whether triangle MNO, so here's MNO, determine whether it is congruent to RQS. So I'm going to look. So notice that these are drawn, one of them is rotated, so that makes it a little harder. So what I'm going to do is I'm going to see, do I have that side angle side, or that side angle side, or that side side side, or that angle side angle? I'm going to go back to our picture. I notice that they both have the 6 side here, the 6. Then they each have a 90-degree angle right here and right here. And then they have that same side measure of 8. So it appears that these are congruent by side angle side. I could also use the Pythagorean theorem on these. So since both of those are right triangles, I could use the Pythagorean theorem to find the missing hypotenuse. They each are missing the hypotenuse. So if Pythagorean theorem, I would find 10. So I could also prove those are congruent by side, side, side. So I could prove side, side, side because the Pythagorean theorem tells me the hypotenuse is 10. I would have to do a little math. I also have my side angle side that I could use. So here we have another one. Determine whether GHI is congruent to JKL. So I'm going to look. It says they're not congruent. The angle measures are not the same. So if you just glance at those really quickly, it looks like they are. But here I want to show you why they are not. So if I look, I'm going to look, I have my 37-degree angle, my 37-degree angle. Then I have my angle. Then they each have the side of 45. But then the next angle, I have 107 and 105. So it looked like it might be angle, side, angle. But these two angles were not congruent. So I cannot prove the triangles are congruent, so they are not congruent. So what we just covered there had to do with congruent triangles, meaning exactly the same. So now we're going to look at what's called similar triangles. So similar triangles means they have the same shape, but not necessarily the same size. So it means they are proportional. So here's an example. So like if I took this triangle here and I were to duplicate it. So right here, the two triangles I just drew, those are congruent. They are exactly the same. If I were to stretch and drag here, now they're no longer congruent, but they're similar because I'm keeping the same angles here. I'm keeping that same basic shape, but they're different sizes. So they're no longer congruent, but they're similar. So in similar triangles, the measures of corresponding angles are equal, and corresponding sides are proportional. So what that means, so if I look at these two blue triangles here, if you are told they're similar, that means, so let's look here. So if I took side A over side D, that gives me 3 over 6. So A over D, I look at 3 over 6, which reduces to 1/2. So that 1/2 should work for every pair of sides. So for example, if I took side B, 5 over side E, 10, 5 over 10 also gives me 1/2. So if I took the remaining sides, 8 over 16, I should also get 1/2. And I do. So that is what happens when triangles are similar. It's what's called proportional. The two triangles are proportional to each other, but not exactly the same, which would be congruent. So if I have two triangles and I say that they're similar, I can use proportions to find missing sides. So the first thing I'm going to do is practice looking at the ratios and the proportion. So it says find the ratio of corresponding sides for similar triangles QRS and XYZ. So I'm told they're similar. So since I'm told they're similar, I know the ratio is 9 to 13. There we go. That's the ratio, 9 to 13. So now we're going to use that to solve for missing sides. So given that the triangles are similar, so that's important, I'm told that they're similar, find the missing length x. So what I'm going to do is I'm going to set up a proportion. So just like before on this example, where I got the 1/2 every time, I'm going to set up a proportion. So what I can do is I could say that 5 over x equals 9 over 6. So I got the slanted side here over slanted side here is bottom here over bottom here. I could also say something like 9 over 5. So if I decide to set it up this way, 9 over 5, I would have to equal that to 6 over x. So this is actually the same proportion. It just kind of depends on how you look at it. So notice I took the right over the left equals the right over the left. I could set it up and say 5 over 9 equals, if I did it that way, I'd have to say x over 6. So I'm just keeping them lined up and corresponding. So in all three proportions that I've written here, I will get the same answer. So here I am solving for x. So I'm going to do something that's called cross multiplying. So what that means is I'm going to literally multiply across. So anytime you have a fraction equal to a fraction and you're solving for x, you want to cross multiply. So when I cross multiply, I'm going to multiply across. X times 9 is just 9x. I multiplied x times 9. You set that equal to what you get when you multiply the other way. 5 times 6, which is 30. So that's called cross multiplying. I multiply across, set it equal to multiplying across. So now I have an equation that's pretty simple to solve. I have 9 times x equals 30. So I'm going to divide both sides by 9. So x is going to be 30 over 9, which reduces to 10/3. So I've got my math here. 10/3 or 3 1/3. So in all of these cases, however I set up my proportion, it's going to work. Here I would have had 30 equals 9x. So notice it's the same equation. So what you have to be careful with when you're setting up the proportion though, is just making sure that you're keeping it like in the same order. So what I would not want to do is say 5 over x equals 6 over 9. So that wouldn't work because notice the 5, I started with the top triangle over bottom triangle. So this should be top over bottom, so that would need to be flipped. Practice definitely helps with these, so when you're doing your homework. So, time for another word problem. It says Tammy Schultz, a firefighter, needs to estimate the height of a burning building. She estimates the length of her shadow to be 8 feet, so I have this 8 feet drawn here, right here. The length of the building's shadow is 60 feet, so I've got that drawn. Find the approximate height of the building if she is 5 feet tall. So people really do measure things this way, like you can measure the height of a tree by measuring its shadow, because it would be proportional, because the sun would hit both you and the tree at the same angle, or the sun would hit the building and the firefighter at the same angle. So you can measure something flat like a shadow to estimate the height of a building. So here I'm looking for the height of the building, which it looks like is labeled as N. Just drew over it. So I can do that once I recognize that I have two triangles, and once I know that they're similar, and they're similar because the sun would be hitting them at the same angle. So I'm going to set up my proportion. So I got to decide how I want to set it up and then be consistent. So if I'm going to say 8 over 5 for that smaller triangle, I got to think about, well, what was the 8? Oh, the 8 was the shadow. And the 5 came from the height. So if I'm going to do shadow over height for the little triangle, I need to do shadow over height for that bigger triangle. So I would need to do 60 over n. So let's say that you did it differently and you said over here, maybe you said 5 over 8. Then you would need to, for the second triangle, write n over 60. And we'll get the same answer either way. So I've got a fraction equal to another fraction. That is when you cross multiply. So 8 times n is 8n. And I want to set that equal to what I get when I multiply across the other way. 60 times 5, which is going to be 300. So to undo multiplying n by 8, I will divide both sides by 8. 300 divided by 8 gives me 37.5. So 37.5, and I think about, and that makes sense, 37.5 feet seems reasonable. If I got something really small or gigantic, that would not make sense. Here's my 37.5, and here it is worked out. So that is all for these two lessons. So remember, there are additional videos on MyLab Math if you need more help.